Hello and welcome to this IB Maths Intense session. This is our sixth video around the topic of sequences and series, and in this video we'll be looking at the idea of the infinite geometric series. This is an interesting topic that you'll see there on the syllabus guide under SL 1.8, sum of infinite convergent geometric sequences, and you'll see that it links to the work that we were doing in the previous two videos on geometric sequences and series there, SL 1.3. What are we talking about when we talk about an infinite geometric series? Well, we're interested in what type of geometric series it is in order to know whether we can find the sum of an infinite geometric series. And there are two sorts of geometric series that we're interested in, and here are the two examples. So in the first one, 2, 4, 8, 16, 32 and so on, we've got a common ratio here of 2. That means every time we add a term, we're doubling the size. So the sum of this geometric series is getting bigger and by larger amounts every time. So if we draw that, we can see the sum of the first term is just 2, just a small block. But then the sum of the next two terms, the first two terms, becomes 6, so it's bigger, the sum. And then the next one is 14, so it's becoming bigger again. So it's gone from 2 to 6 to 14. Hopefully you're getting the point. Then add 16 and it's going to become even bigger again. It's going up to 30, and then I'm going to add 32 and it's going to go all the way up here. It's going to go to 62. This is called a divergent series because its total is always moving away from the starting point at a rate of knots. It's always getting bigger by a larger amount. It's in this case, you can see from the diagram, significantly bigger total every time we add another term. But have a look at the next example, B, where this time we've got a common ratio of a half. We're halving every term. And this time when we look at what happens to the total, what happens to the result of the series, we'll see that the opposite happens. So in this one, when I have my first term, the sum there is 32, and when I add the next term, it goes to 48. So it doesn't appear as big an increase, and then it goes to 56, which is even closer, 56, and then it only goes up to 60, and then only up to 62, and then up to 63, and this distance between the totals is getting smaller and smaller and smaller every time. It's a convergent series, and in fact the total will converge on a particular total, which it doesn't really matter how many terms you add after that, the total is never going to get bigger than that. And I can illustrate that with this example B. If we just look at a simple case of the sum of those 5 terms that I put on there, using the formula that we've got for the sum of a geometric series, that would be S5 equals, this is just using this formula here, S5 would be 32 times 1 minus a half to the 5 all over a half. And that gives us a total of 62. If I move along the series and say, look at what happens after 10 terms, I'm going to have 32 times 1 minus a half to the 10 all over a half. And this time, the total is only a tiny bit bigger. It's 63.9375. And if I go even further, S20, 20 terms now, 32 times 1 minus a half to the 20 all over a half, you'll see the total has barely changed. It's 63.9999. So if we imagine that we had gone all the way to infinity, or as close as we could, our sum to infinity would be equal to 32, and then 1 minus a half to the power of infinity. A half to the power of infinity is going to be so small, it's pretty well 0. So it's basically going to be 32 on the top, because 1 minus pretty well 0 is 1. And then on the bottom it's going to be a half, and the sum to infinity there would become 64. And you can see from this picture here, and you can see from this total here, that the sum as we move towards infinity, gets closer until it reaches, but never gets bigger than, 64. And indeed, what we've just done there is basically derived the formula for the sum of a convergent or infinite geometric series, because what we've said is that as we get further along the series, we can ignore the 1 minus r to the n, because the r to the n is so small it doesn't really exist anymore, and we end up with s to infinity is u1 over 1 minus r. And that is our formula for finding the sum of an infinite geometric series. Now, here's the formula sheet as I currently have it from the IB, and you'll see that they've written the formula like this. S to infinity equals u1 over r minus 1. And I'm just going to put a big cross through that and say, no, that's not the correct formula. It should be s to infinity equals u1 over 1 minus r. The other formula is not correct, and hopefully that will be repaired on the formula sheet for by the time you get to do your exams. It also says here, this particular expression here, this reads as modulus of r is less than 1. The modulus of a number basically means its absolute value, so without a plus or a minus sign. And another way of writing that is to say that means that r must sit between minus 1 and 1. So in other words, our common ratio is a number between 1 and minus 1, which means that the next term in a geometric series will always be getting smaller, because the common ratio sits between 1 and minus 1. So if I just draw a quick example, this one, 200, 150, 25, and so on, 12.5. My first term is 200, my common ratio is a half, hopefully nice and straightforward. And our sum to infinity here, you can almost guess it just from looking at the numbers, would be just 200, my value of u1, divided by 1 minus a half, which is a half. And so my sum to infinity here is 400. Doesn't matter how big this geometric series becomes, its sum will be 400 once we get past a certain number of terms. So with that formula, it's very easy. S to infinity is equal to u1 over 1 minus r. Then we can look at a number of different styles of questions that we'll be expected to do. So here's an example. The first term of a convergent geometric series is 40. This is telling us that the value of r must sit between minus 1 and 1. And its sum to infinity is 53 and a third. So find the common ratio. So let's write down what we know. The sum to infinity is equal to 53 and a third. u1 is equal to 40. So we got the sum to infinity, 53 and a third, by calculating u1 over 1 minus r. And just a little bit of rearrangement here, and we can solve this pretty quickly. 53 and a third multiplied by 1 minus r to get rid of the fraction equals 40. Expand all of that out. 53 and a third minus 53 and a third r equals 40. If I rearrange that now, I end up with 53 and a third r. I've moved that to the other side, and I'll subtract 40 from the 53 and a third to give 13 and a third. Hope you're with me there. And then we can calculate the value of the common ratio. R equals 13 and a third divided by 53 and a third, which is equal to 1/4. And sure enough, a value of r sits between 1 and minus 1. So we can work backwards and find the common ratio. What else might we be expected to do? This time we're told the sum to infinity is 6. The second term is minus 8 over 3. And again, we're asked to find the common ratio. Now here we have to do a little bit more work because we don't know what the first term is. So again, we can write down what we know. The sum to infinity, which is equal to u1 over 1 minus r, is equal to 6. We also know that the second term, u2, That is calculated by multiplying the first term by the common ratio. And we know that u1r must equal minus 8 over 3, because we're told the second term is minus 8 over 3. Now this is where we can solve by creating an expression. Let's create an expression here for u1. u1 must be equal to minus 8 over 3r, because I'm dividing by r. And then I'm going to use this value for u1 and stick it in this particular expression here. So 6 equals u1, which is minus 8 over 3r, all over 1 minus r. And I should be able to find the common ratio now just by working that through. So just going to multiply by 1 minus r. 6 times 1 minus r equals minus 8 over 3r. And then going to multiply by 3r. 18r times 1 minus r equals minus 8. So that's 18r minus 18r squared equals minus 8. Let's put all of that together. We'll go up here and make that into a nice quadratic. 18r squared minus 18r minus 8 equals 0. I've taken the 18r squared over to the other side so that it's positive, and I've taken the 18r with it. I could halve those two, just those three terms, sorry, just to make this a bit easier to factorize. And then if factorizing is good, you can put that into double brackets. If not, you could use the quadratic formula. But either way, it factorizes to 3r minus 4 times 3r plus 1 equals 0. Now there are two roots for this. So r is either equal to, well, from the first brackets, r would have to be equal to 4 over 3. Or, second bracket, r would have to be minus a third. Now, since modulus of r has to be less than 1, in other words, r has to sit between minus 1 and 1, r must be equal to just this one, minus a third, because this other one does not sit between minus 1 and 1. Last example then, just working in all of these cases with the formula and using the information we know about different terms in a sequence. We're told this time that the first term is 128, u1 equals 128, and the seventh term, u7, equals 2. It has two possible sums to infinity, this sequence. We asked to find them. So let's write down another expression. u7 equals 2, and u7 is calculated by multiplying u1 by, which is 128, don't need to write u1, it's 128 times r to the 6th. So we know that 128 r to the 6th is equal to 2. So I can work backwards. R to the power of 6 is 2 over 128, which is 1 over 64. So r must be equal to, now the sixth root of 1 over 64 is plus or minus a half. Because it's an even power, it has positive and negative roots. So r equals plus or minus a half. So we have two sums to infinity. So number one, we have a sum to infinity which is equal to first term 128 over 1 minus r, where it's positive, 1 minus a half, which is equal to 256. Or alternative, number two, sum to infinity equals 128. This time it's going to be 1 minus a half. So it's going to be 1½ on the bottom, or 3 over 2 on the bottom. And if I work this out, I get 85 and 1/3. So there are two possible sums to infinity here, depending on whether my value of r is positive or negative. So there are a few questions playing with the formula, working backwards and forwards. Hope you found that useful. This is the idea that a convergent series tends towards a sum to infinity, and there at the top there is the simple formula, not the one on the formula sheet that you should use. Hope you found that useful. Thank you for watching. Don't forget to like this video and subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here. Drop me an email at ibmathsintense@gmail.com if there's anything you'd like to see, any questions, if you spotted any mistakes or any observations you'd like to make. But in the meantime, enjoy your maths and take care.